Hi, welcome to CreepGame Assignment 2.08, the final assignment for the semester. Here are requirements. In our tool code, we want to organize all the static collision data into an Octree. And then in our game, we want to send all of our raycast operations through that Octree as an optimization step. Currently, we're using a brute force approach, which basically does a raycast operation against every single triangle in our static collision data. And we can do much better than that. So let's take a look. Okay, here's our solution. Run the game. Now, unfortunately, the nature of this game doesn't give us much to show. I'm sorry, the nature of this assignment doesn't give us much to show in the game. However, I did add a little bit of stat data, and the interesting thing here is this number of primitives. Basically, the player right now is in a particular Octree node, and there are a certain number of primitives, namely triangles, in that node. This particular node that I'm in right now, there's 0. And if I move around a little bit, you see now there's 6 in this particular. I moved into a different node here, and there's 6 of them, 6 triangles being existing in this particular Octree node. And now there's 4 in this one. And then here we see 30. Okay, but that's not so interesting. Let's take a look at some code. So here's the code which reads in all the scenes. Here's our collision scene, but we also see the humanoid monster, the cube, and so on. And here's the actual call that reads the data in, and we do some processing of it here. And down here we get into some Octree stuff. We basically get a pointer into the Octree info for the collision data. And using that pointer, we get a bounding box for the Octree for the collision data, and then we get a center of that bounding box, and we get the extents of that bounding box. Let's run this and see what kind of values we get here. Okay, so we see that the center is at, it's almost the so the center for the bounding box, which is around the Octree, it's almost centered at the same center as the game, the 0, 0, 0 center, I mean. And if I hit F10 here, I can see that the extents are basically, it says we've got about 1760 in the X and Z directions, and quite a bit less in the Y direction, so it's sort of compressed in the Y direction. Let me get out of this. Okay, now notice there's a couple of commented out lines here, and we're going to look at this one first. So this one basically says let's draw a cube of our Octree information based around the center, and let's use these extents. So basically it's a big cube of this size. So let's uncomment this line, and we'll build it and run it. And this will show lines which will allow us to actually visualize our Octree nodes. Except that I'm not sure this. Okay, there we go. So now we see a bunch of lines in here which show us which the actual nodes themselves. You get a feel for the size of it. Now I believe I'm using an Octree depth of 3 or 4. Let's fly outside of this whole arena here. Take a look back down at everything. So there you go. So there's our 1750 by 1750 by 1750 bounding box, and it contains all of our scene data in there. And let's get a look at the colors here. The colors actually show us some information. Now this white outer box is the depth 1 Octree. Basically it's the entire thing. And now you'll notice this blue line in the center, that's our depth 2 divisor. In other words, it cuts the outer one into 8 children. And then the red box cuts each of those children into 8 more children. Then the green box are those 8 children of the red children. So you get kind of an idea here. So what is it? It's white, blue, red, green. So that's a depth of 4, Quadtree depth of 4. And we notice that it pretty much encapsulates the entire thing. So we had to make the box really big in the Y direction, bigger than it needs to be, because the X and Z directions extend so far. Okay, now let's get out of the game and let's comment out this line again, and let's notice the line above it. Now this line basically says draw the data, but instead let's use the bounding box center and the bounding box extents. So let's compile that and run it. Once again, we'll see all the nodes and all. It'll look pretty much the same from inside the game, but let's fly outside, take a peek, turn around, and we see that we've actually narrowed down right onto the structure of the game arena. But those lines are really more concerned with collision data, and what we're showing is scene data. So let's go into the debug menu and turn off the scene data and turn on the collision data. And now we see that the bounding box is a perfect fit for the collision data. And so what we've really done here is we've optimized that huge bounding box to be just the bounding box we need. So all of our nodes, all of the data that we process is just what's inside of this bounding box that we're showing here. Okay, so let's get out of this and look at some more code. So the first code we want to see, let's take a look at how collisions work. So we've got this collision tester, and it's got a method called find wall. And basically the purpose of this method is you shoot a ray cast in a certain direction, this direction here, and this find wall will tell you the distance to the closest wall in that direction. And let's see how it does that. So we do a little bit of setup here, but here notice you see we're using the Octree, and we're calling a method called traverse ray hits. So we're basically going through the Octree and saying follow all the Octree nodes, find out where this ray intersects stuff. So let's go take a look at that. And we see here that we're in the octree.h file, and you'll notice here we've got a template. I've templatized all of my Octree code basically. So here's the traverse ray hits, and what it's doing is calling it its own private version and passing in some extra data. Now the reason I do this is because I want to set it up to do some recursive calls, and it's just easier if the outside interface doesn't need to know about the recursion, so it's taken care of by the inside interface. So let's go to this private version of the traverse ray hits. Okay, so here we go. Let's ignore this for a second. So every node in an basically, actually, let's take a quick look at this. Notice this says this is the way out of a recursive function. You say, have we gone as far down as we can go? And if so, then do this other stuff. But we'll look at the other stuff in a second. So basically, since we're not at the bottom yet, the current node that we're in, the current node we're processing, has 8 children. And so this loop here is going to loop over all 8 of the children, the oct children nodes. And so what it does is it gets the bounding box for the current child, and it sees if there's any intersections between the ray and that bounding box. In other words, it basically just says, does the ray that we're casting, does it even intersect my child box, the entire box? Who cares what's in it? Does it even intersect it? Because if it doesn't intersect it, we don't care about anything further down there. We can just throw that whole thing away. So you see we're saying here, if it does not intersect it, then just continue, go to the next child basically. So if we come down here, it means we are intersecting, and here's where we do the recursive call. It basically says traverse again deeper, in other words, do the 8 children of this child, and here's where we add one more to the depth. And eventually we're going to get to this max depth. In other words, as long as we find hits on these children, and we get a hit on one of its children, and a hit on one of its children, and so on, all the way down to the bottom. If there's a hit on the very lowest node, we're going to call this callback function, basically saying, hey, we followed this guy all the way down, and your ray is going to hit something in here. If it may hit something in here, you need to check all of the triangles that are in this particular child node. So let's find out where we got that callback. That callback was actually passed in right here. This test ray triangle was the callback we passed in. So let's go there. So here's the function, test ray triangle. So basically this thing is waiting to be called with the index of a cell that may or may not, I'm sorry, a cell that the ray does intersect, and it may or may not have triangles in there which may or may not intersect. So what we're going to do is we're basically going to call this, test this ray against all the triangles in this Octree cell. And so let's go to that code, that test ray triangle. Okay, so this triangle, so basically one of our nodes has information in it about the triangles that exist in that node, the primitives existing in that node, and this code here basically figures out how to access the pieces in that that child node so that we can walk through them. So basically it's saying in that node there are some number of primitives. So so this loop is basically saying for each primitive in that node, let's see if the triangle intersects, if the ray intersects a triangle, and let's do it for all the triangles in there, and let's find the closest one to the center from the point that we're testing this cast from. Let's find the closest triangle that that ray from that point actually intersects. So so here we're doing it for each triangle in that data. We're basically doing a ray intersect with that triangle. So we're saying, does the ray actually intersect this current triangle? And we've got all the verts and stuff here. And if it does, is it closer than our current closest one, which is initially set up to be a very large value? And if it is, let's keep track of it. And we also handle here, it says reverse the triangle in case the artist got it backwards. There are some triangles in here that are actually backwards. So you'll notice here we pass the points in, point 0, 1, and 2. Well, here we're going to turn them around the other way and see if it intersects that triangle, because maybe it was coming in from the back of the wall, because that particular triangle was backwards. So we're handling this Easter egg case here by saying the points maybe were in the P2, P1, P0 order. So basically this code here is finding the closest triangle that the ray intersects in this particular Octree node, if any. And I know that's kind of a lot to absorb, but that's my overview for assignment 2.08, CreepGame Assignments 2.08. Thank you and goodbye.